Thank you. So since this is the first talk in the ideal cipher session, we can start with this slide. So about what is a block cipher. So a block cipher is a block that takes a key here at the bottom and an input and an output. For each key, it induces a permutation between the inputs and the outputs. And that's a block cipher. So all these wires, you can think of them as being like n-bit values. So the key is n bits, the input and output are n bits. Maybe the key would be something different in general, but we can think of this as being n-bit values. So more particularly within block ciphers, we're interested in a particular design rationale for block ciphers, like a particular way of making them. So a block cipher is an exponentially large family of permutations, one for every key, and there's exponentially many keys. But say I've constructed just a finite number, just a few very good permutations that I like. Here they're on my drawing, they're P1 through P5. I've just constructed 5 of them, and I really like these guys. They're good. And then the way that I use the key is I just put these permutations in a row, and I XOR the key between each of them. And this way, the key influences the permutation I get, and whatever. I call this key. This is one way of constructing a block cipher. I call it a key alternating cipher. So a little more generally, we could pass the key through a key scheduler. So we don't need the same key at every round, the same subkey at every round. We can take the key and process it any way we want. And so we could have like an arbitrary key scheduling mechanism. And each one of these key schedulers, so here I have 6 different key schedulers. I mean, they don't have to all be the same. Each key scheduler could be something a little bit different. OK, so why do we care about key alternating ciphers? Well, for one, for example, very prominent block ciphers are key alternating ciphers. For example, AES is a key alternating cipher. So AES is 10 rounds. And it uses actually the same permutation over and over again. So not 5 different permutations or whatever, but the same permutation 10 times. And it's this famous Reindel or whatever, sorry for my pronunciation, round function in which the subbytes, the shift rows, and mixed columns, that famous one. And so that's, for instance, a key alternating cipher with some specific round function, some specific key scheduling function. And basically, block ciphers tend to fall into 2 different families, either Feistel-based or key alternating. And the more modern ones tend to be actually key alternating. So it's interesting to look at key alternating ciphers from the point of view of provable security. And so I'll tell you a little bit about what's been done, which isn't that much, or mostly it's been very recent, except for this one thing from 1991. So going all the way back, we have the Even-Mansour Cipher, which is, they just propose to take one permutation and XOR like a pre-whitening key at the beginning and a post-whatever key at the end. And so here the key is actually 2 n bits long. So the key consists of n bits is k0 and another n bits is k1. And they say, why don't we build a block cipher like this? So 2 n-bit key, and that's our block cipher from some permutation p that we like. And they argue the security of this with the following experiment. So they consider the following real world and ideal worlds. In the real world, the distinguisher gets oracle access to P, which is modeled as a random permutation. All right, this is the random permutation model. And it also gets access to E sub k, which is the Even-Mansour cipher. So this E sub k is this construction up there, all right? And in the ideal world, it also gets access to random permutation P. But instead of E sub k, it just gets a podunk, just some other random permutation that has no relation to anything. Q is just another independent random permutation. And they argue that, they show that these 2 worlds are indistinguishable up to q to 2 to the n over 2 query, so up to birthday bound, basically. So these 2 worlds will look the same. So this E sub k, despite the fact that it's built just from one random permutation P, looks like an independent random permutation up to a certain number of queries. So this is, I forgot to emphasize, this k here is randomly chosen, fixed, and hidden from the adversary in this experiment, all right? OK, so that's this first result about key alternating ciphers. Then the natural thing to do, maybe from here, is to look at the extension of this to multiple rounds. So there's the, sorry, guys. Here's actually, I'll use this fact in a little bit. So a fun fact is that this bound still holds if the keys are the same. You don't need 2 n bits of key. You can get away with n bits of key. They don't put this in their original paper, but it's clear from the proof. OK. So this is the generalization to T rounds. So here I have K0 through KT, and the key is just this long, each one of these guys is n bits. So this is a T plus 1 times n bit string. That's the key. And I can consider the same experiment, basically. In the real world, I have Oracle access to the T permutations, which are each one modeled as independent random permutations, plus the block cipher for some fixed random and key k that's hidden from me. As a distinguisher, I don't know what k I'm working with. And in the ideal world, I just have basically T plus 1 independent, completely independent random permutations. Q is just one extra independent random permutation. So results on this go as follows. So I mean, the Even-Mansour goes back to 1991, but for some reason, looking at T greater than or equal to 2, people took a while to realize this was maybe an interesting question. And so the first results are from 2012, strangely. But Bogdanov and co-authors, they show they improved the 1/2 times n to 2/3 times n for T greater than or equal to 2. Later, I improved this to 2 to the 3/4 times n for T greater than or equal to 3. So you see the pattern goes, for T equals 1, it's 1/2 times n. For T2, it's 2/3, then 3/4. Actually, the conjectured optimal is T over T plus 1 for T rounds, OK? So that's what's going on. So actually, these 2 bounds here are sharp. This first bound is sharp for T equals 2. The second bound is sharp for T equals 3 as far as these indistinguishability results go. And then there was Rodolphe Lampe, Jacques Patarin, and Yannick Serin almost got that T over T plus 1 times n, but not quite. But that's OK, because it gave me and my student the opportunity to get it. So this question is over now. So this is a nice success story in indistinguishability. We know we have the sharp upper, we have a matching attack, and so this indistinguishability of key alternating ciphers in this model is done. That's nice. But anyway, the problem, actually, it's not that nice, because indistinguishability is not all that great. I have to argue this now since I'm presenting another result. So why is indistinguishability not all that great? So let me give you an example. So here's the Davis-Meyer compression function. It's a way of compressing stuff using many hash functions. So it's a very fun, very basic thing. You take a block cipher, you have the input. So I use it as a compression function the following way. Key input and word input, I apply the block cipher to the word, and then, so E sub k of x, and I XOR with x to sort of make it pre-image resistant. And actually, this turns out to be collision resistance. It's easy to prove in the ideal cipher model. So if you expect that if you have a good cipher, this will be collision resistant, because it's collision resistant in the ideal cipher model, this compression function. But if you use it, for instance, with this Even-Mansour guy, let's say, that was proved indistinguishable in that experiment, it's not collision resistant. So this is what it looks like when I replace the block cipher by Even-Mansour. And if you look at it algebraically, the expression is that this Davis-Myers of kx becomes p of x plus k. Yeah, here's p of x plus k. And then we XOR at the end is, again, x plus k. And if you look at that, you probably see it's not collision resistant, because all I need to do to get a collision is to choose another value x prime k prime, such that x plus k is equal to x prime plus k prime. And then it collides. I don't even have to make any queries. I can announce to you a collision without making any queries to anything. All right, so this is obviously not collision resistant. So this Even-Mansour cipher, despite being blah, 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 having these indistinguishability properties when you have a fixed random hidden key, it has many other properties you would like it to have just aren't there when you're working with many different keys at the same time. Okay, so you want something stronger where you're allowed to work with different keys at the same time. And really the strongest thing you can aim for is this indifferentiability notion. So this is the what's indifferentiability again slide. So I'll briefly attempt to describe it. So it's again about proving the indistinguishability of 2 worlds, but now there's a real world and a simulated world. So first let me go with the real world, which is easier to describe. So in the real world, I want to have Oracle access again to the permutations P1 through PT, which are modeled as independent random permutations, and to the key alternating cipher itself. Except, there's a difference now. The key alternating cipher, I have control over the key. I can query it for the key I want and for the word I want. Or the inverse, the E minus 1, I can query it for the output I want and the key I want. So this is a much more sort of powerful set of oracles than before, because I'm not stuck just using one specific key as my oracle. Now, the simulated worlds, first let me show you what E is replaced with. In the simulated world, E is replaced with an ideal cipher. So it's just for every key an independent random permutation. And that ideal cipher doesn't want to ask queries to anybody. I mean, it's an independent thing. It lives on its own, OK? So what's going to replace the permutations P1 through PT is a simulator. It's going to be taking responsibility for P1 through PT. And basically, the simulator takes queries that are destined for P1 through PT and does its best to invent answers such that these two worlds are indistinguishable. So when you prove an indifferentiability result, you have to come up with a simulator such that these two worlds look alike. So for instance, D may ask a query to E and then verify that query using P1 through PT. But what happened in the simulated world is that E would be asking that query to the ideal cipher and then verifying it by asking the simulator. The simulator, as it sees queries coming at it, better figure out what query D is trying to verify. And in order to be consistent, make it look like the real world, it should ask itself, it should make a query to the ideal cipher to make things look consistent, sort of. That's basically the idea. So the main question is for how many rounds and for what kind of key scheduling is a key alternating cipher indifferentiable? Actually, so it's good that I mentioned this, what kind of key scheduling, because the key schedule, I didn't mention it recently, but it could be idealized too. It could be like the key schedule could use a random oracle or random permutation or something. So if it's idealized, it should be included as an oracle itself. Okay, so here I put an extra little gadget for the key schedule, and it also falls under control of the simulator. So this is our main question. So the main positive is that actually 5 rounds with a random oracle key schedule is indifferentiable. So here you go. So each of these E's here is a random oracle, and they're actually all the same. Okay, so all of the 6 E's are the same key random oracle. And also another thing we prove is that 5 rounds where the key schedule is replaced, so this random oracle is replaced by a permutation with a feed-forward XOR, so a permutation in DM mode is also indifferentiable. So that's kind of nice because it means you can build your ideal cipher, build something that's indifferentiable from an ideal cipher directly from just 6 fixed permutations. It's the first direct construction of a block cipher directly from permutations without going through an intermediate step. Yeah, through random oracles. And anyway, so it's a certain security, a certain query complexity. Running time won't go through that because I'm already running short on time. So there's some negative results. For instance, that 2 rounds with any key schedule is never going to be indifferentiable, no matter what. Yeah, and then 3 rounds with a certain class of key schedules is not indifferentiable either, but I'm not so interested in discussing the details. Actually, I'm going to hide these results. Here's actually, this is kind of interesting. So there's a follow-up result coming after ours by Lampe and Serin that 12 rounds with no key scheduling, but you use an identical key at every round, okay? There's actually 13 slots where you XOR the key. This is also indifferentiable, so that's kind of cool. So if you can use a random oracle key schedule, you can get everything down to 5 rounds. If you're without the random oracle key schedule, you're sort of blowing up to 12 rounds. This one has worse bounds, but whatever. OK, so let me talk about now how our simulator works. But maybe first, before talking about how the simulator works, talk about, to understand how the simulator works, it's good to think about how the distinguisher might attack and try to distinguish. So let's talk about attacking instead of about simulating. So say I'll describe an attack. The distinguisher chooses some value x at random. X will go out here on the left, and the key k at random. Okay. It queries the key schedule function on k. This is the simulator sees. The simulator is responsible for the key schedule. So it gets this this output here on the red on these wires here, the vertical wires. Now it knows all those values for that key k. It's all the same value. And also it knows this input to P1, right? Because it chose that x and it knows this input to P1. I'm just going to go left to right now. It's going to query P1 on this value, this x plus the subkey here. Just gets a value out here, gets this value y1, and just going to go from left to right. It queries P2 on the corresponding value, gets the value y2. And it knows all the subkeys, so it can just keep going. And so the simulator sees all these queries. Anyway, it goes all the way to the end here. And then at the end, the distinguisher checks that the final value it got, this y5, is compatible with the block cipher, that y5 plus the subkey, which is this value all the way at the end here, is equal to what its block cipher oracle tells it. So it constructed a chain, and it verifies the consistency of that chain with its block cipher oracle. Okay, it constructs a chain. So you can imagine the distinguisher constructing chains like this in many different ways. Here it started all the way at the left, and it went all the way to the right, but it could maybe start somewhere at the beginning, like at y2, and then spread left and spread right, and check at the endpoints. Okay. It could maybe start at y1 and go left first, but then wrap around using its block cipher oracle, and then keep on going from the right and meet up here again. It can do things in all sorts of orders to construct a chain and see if they meet correctly, all right? And it can mix and match this, doing this with different subkeys at the same time. So it could choose a certain value y2 and use it with 2 different subkeys and so on and so forth. And so this is what the simulator is up against. This distinguisher trying to construct maybe lots of chains at once, very confusingly, and some of them are going to match up, and the simulator has to make those match up by making queries to the block cipher. So the simulator is going to use, we're going to use the following thing, this Tripwire Paradigm, to help it like detect chains and decide when to complete a chain preemptively. So imagine the following situation, very specific, okay? Say that P of x1 equals y1 is an already made P1 query. So this query has been made. By the way, I should comment, this little green thing here is a grenade, right? I looked for, there's no good like images for tripwires, okay? But this has the connotation of an explosive device, right? So a grenade with a dotted line going through it is good enough. So we have a P1 has this already made query. We have another query is being made right now to P2. This P2 of x2 is being made right now at this instant. And this value x2 plus y1 is an already scheduled subkey. Okay? Then if all these whatever conditions are met, and we've installed this particular tripwire at this particular position, this particular direction, symbolized by this symbol, then the simulator, at this point, seeing all this stuff, lunges forwards and completes a chain, meaning it'll preemptively define P3, P4, P5 for this chain and make it match with the block cipher. Okay? This is what it means to have this so-called tripwire here. It means that if the P1 query and then a P2 query come along, so P1 first, then P2, and they match with a subkey that's already been scheduled, then you go ahead and complete a chain. That's the idea. So this thing is called a 1-2 tripwire because it's between positions 1 and 2. You could consider a 2-1 tripwire, but that would be only triggered if you make the P2 query before the P1 query. So in this case, with all these conditions satisfied, if you have a 2-1 tripwire, you would not lunge forward and complete a chain. It's not symmetric, okay? So anyway, for this tripwire thing, oh, I'm at 0. How many minutes do I have, actually?
Well, you have 1 more minute, but then there won't be questions.
Okay, sure. So I'm glad to know you don't have any questions. So here's the basic challenge with installing these tripwires. So install enough tripwire to be secure so that you complete chains that the distinguisher is trying to form. You actually complete them, but you don't install so many tripwires as to blow yourself up. What does that mean? If you install too many tripwires, you're going to recurse yourself. I mean, yourself, as you make queries, you may trigger the tripwires, and you may trigger even more, and you may never terminate. You may diverge. This is what the simulator then blows up. Okay, so you have to install enough, but not too many. This is the real trick. This is our solution, 4 tripwire solution. 2 tripwires sort of around P2 in either direction, 2 tripwires around P4. I guess I'll just do one sample case. So say the distinguisher schedules a key, chooses a value out here at the left, goes forward, makes a query to P1. So far, no tripwires have been set off. Goes forward again, makes a query to P2, does not set off this tripwire. Goes forward more, then it sets off a tripwire, right? You get it? Because between P2 and P3, there's a left to right tripwire, and then it would set it off, right? Another example, you start between P2 and P3. You first make the P3 query, no tripwire set off. You make a P2 query, still no tripwire set off. You make a P4 query, still no tripwire set off. But now you're sort of stuck on either side. If you go here, you'll set off a tripwire. If you go here, you'll set off a tripwire. That's the basic idea of the simulator. OK. So now we're done, and I'll take no questions. Thank you.